Okay, guys. So, yeah, this is the second copy for the algorithm analysis. In the previous copy, I talked about how you can use notations like big O notation, big omega notation, and theta notation to analyze functions. All right. So here, let's talk about how we can use those notations to analyze algorithms. All right. So, uh, yeah. Before we get started, this is something I think I forgot to mention in the last copy. Uh, so let's say that there's a function like this. Okay, you guys can see this, right? Yes, you can. So there's a function like this. So fn is this, and we need to find value of gn. Okay. So either for big O or for could be for big omega, anything. So the way we can find gn is that we find the most dominant term in this expression. In this one, it's this 3 times n cube term. This is the most dominant term, and we take the most dominant term and remove all its coefficients, and then we say gn is equal to that value. So that's 3 actually. So yeah, like this. So for this fn, gn is n cube. Okay, that's the easiest way to find this. Okay, so you get rid of the non-dominant terms. So the reason why we get rid of these non-dominant terms is because when becomes a really large value, the contribution these terms give to the final value is uh, it's almost not there. Like let's say that n is 1 million. So if n is 1 million, the most dominant term will be 3 times 10 to the power of 6 to the and then you cube it, and then plus 8. Actually this 8 doesn't contribute at all. The contribution is very small. So the same thing for n squared. All right, so this is 6 actually. So because of that, and we have analyzed this uh, functions as they reach infinity, so for very large values. And when n goes for very large values, the contribution of these non-dominant terms is almost non-recognizable. Because of that, we just get rid of them. The other thing is that we get rid of the coefficient is because we need to find a class a particular function belongs to. So let's say that there's another function like let's call it hn n. Okay, so that one is n cube plus 7. So okay, for this also, if you're about to find the gn, will be n cube. Okay, for both of these functions, okay, this one and this one, we have the same gn value because it's actually about finding the class a particular function belongs to. So in this scenario, it's the n cube class. All right. So we find gn like that. So for this function, we can say, so let's say we found fn. So we can say fn should be n. Fn is big O of n cube. And for this one also, we can say hn is big O of n cube. Same way, you can say big omega as well. Okay, so you find big omega the same way. You have fn, you get the most dominant term, and then you get rid of the coefficient, so you get big omega as n cube as well. Because n big O and big omega share the same gn, we can say theta is n cube. So that's about it. Same thing for this as well. All right. So if you want to make sure that you are correct, you can use limits to look for the value. Okay, so let's try some limits now. So I'm not gonna teach you limits here because there's a copy which Revin did a long time ago. You guys can check it out if you want to. Okay, so uh, it's uploaded to the YouTube. So over here I will teach you guys how you can use limits to find uh, whether Gn is belongs to big of big omega or big of n or big theta theta notations. So the thing is, so there's this notation. We have limit and goes to infinity. That should be infinity. That's better. Infinity fn divided by gn. Alright, it should be g actually. Let's do it. That's better. That's much better. All right. So by solving this, you can figure out whether Gn belongs to big O, big omega, or big theta. All right. So yeah. So before that, there's a couple of mathematical things I need to teach you. So the first thing is, so let's say there's an expression called x. Let's just say there's an expression like 2 plus 4 plus 30. All right. So you can write this by taking the 2 out, which is the common factor, and write it like this. Okay, this is basic maths. This is grade 5 maths almost. I don't know. So this is basic maths. Okay. So you can write another expression like let's say 3 times 9 and 6 and 9. So you can take 3 out and then write it like 1 plus 2 plus 3. Okay, so we are taking the common factor out from the expression. So what happens is, okay, over here, when I take 2 out, what I do is that what I'm doing is that I'm dividing each element by the factor I took out, and then 30. And if you simplify this, you get this final answer, which is 2 times should be bracket 1 plus 2 plus 15. All right. So by using this, we can take any factor out. Okay. So what do I mean by that? Let's write the notation again. Plus 30. So this is what happens if I take 2 out. So each element gets divided by 2. If I try to take, so let's say from this expression, I try to take 5. So if I try to take 5, it will be 2 divided by 5 plus 4 divided by 5 plus 30 divided by 5. You can simplify that to 6. So you can write it like, if you simplify 30 divided by 5, it will be should be bracket. Okay, so it should be like this. So it's gonna be 2 divided by 5 plus 4 divided by 5 plus 6. So as you can see, 5 isn't a common factor for these 3 tokens. but I can take 5 out. I can take any factor out using this method. So if I want to take n out, it will literally be 2 divided by n plus 4 divided by n plus 30 divided by n. So I can take any factor out like that from any expression. So it doesn't has to be a common factor within the expression. You can take any factor out like that. Okay, so this is something you have to keep in mind when I do the limits. I will use this very frequently. And the other thing is, let's say that I'm dividing a value by a number. So let's say I divide 5 by 10. So this will simplify to 0.5, right? So if I divide 5, the same value, by 100, should be 100 on the triangle thing. Let's write 100. I divide it by 100. Okay, so then this will be 0.05. If I divide this by 10 to the power 10, this will be 5 times 10 to the power minus 10. So 10 to the power minus 10 is like 0. Then bunch of zeros, then bunch of zeros, then 5. So there should be 9 zeros, then 5. So what I'm trying to point out is, let's say there is a constant called c, and you divide it by value x. As the value of x increases, the overall value of this expression goes towards 0. So if I it's not straight line. Okay, so let's say I have this number line. Okay, so so I have this number line and I have 0 here, then 0.5 is over here, then 0.05 is going to be over here, okay, somewhere, but then 5 times 10 to the power minus 10, and then if I keep increasing the value, it's going to get smaller, and it's going to keep it's going to go towards 0. So the way we write this is, so let's say there's a constant c divided by variable x. As x goes to infinity, which means that x going for large values, c divided by x goes to 0. So hope that's clear. Okay, so yeah, so as x becomes larger, the overall expression gets smaller and smaller and smaller, and as x goes to infinity is the biggest value possible. It's not a defined value, it's not a countable value, it's a really large value. The expression will go towards 0. It will never be 0, but it will go towards 0. Alright, so that's what we'll be using over here. Okay, so let's say that there's this fn and gn. Okay, so let's say, for an example, fn is n squared plus 5n plus 3. Alright, so we can get a candidate for gn using the method I mentioned previous. I can say gn is equal to n squared. Give me a moment. Alright, so you can get the candidate like this. So you can write it like this. limit n goes to infinity fn divided by limit n goes to infinity gn. So both of them mean the same thing. All right. So what this expression? So let's say that we have this limit n goes to infinity fn. So fn is a function. Okay, so fn is a function that goes like this. So what this expression means, this should be n goes to infinity. Maths, not very good at it. Oh, that's it. So what this means is this gives the value of fn, which is this, as it goes to infinity. So let's say that over here this is what, 100 or something. At 100 the value is like what, 75. So as it goes to infinity, infinity isn't a proper value like 100. It just says that as function goes for larger values, this gives the this gives us the value of fn. So some of you might say that it will always be infinity, because as n goes to infinity, should fn be always be infinity. That's actually not the case, because there are some functions that was not right. Okay, so there are some functions that goes like this. This is a function as well. As you can see, this function as let's say x. For this function, x goes to infinity. Let's call this function hx. Hx should be x. Hx actually goes towards 0. It will never come to 0. It will always go towards 0. Same way. All right. So hope what this notation means is clear. So this means the value of the function as it reaches infinity. So what we are going to do is we are going to divide the value of fn when it's at infinity by the value of gn when it's at infinity. Okay, so that's what we're going to do. I'm going to erase this. Okay, just give me a moment. So what we're doing over here is we are this is infinity actually, just in case if it's not clear. This is infinity. I don't think it's infinity. So what we are doing over here is we are dividing the value of fn when it's at infinity by the value of gn when it's at infinity. So there are three possible values we can get. Okay, so I will do some calculations I show you guys later, but let's talk about the three possible values. The first possible value is that we can get infinity. My goodness, I'm horrible at writing infinity. So let's give it a try. That's better. The second possible value is 0, and third possible value is a countable value. Okay, let's write countable. This is the countable value, like 3 or 10 or could be 100. Okay, it's a countable value. So these are the three possible values we can get for this expression. Okay, let's get rid of this fn as well for now. We won't be doing any calculations. Okay, so for this expression over here, okay, so there are three possible values. One is infinity, one is 0, one is a countable value. So infinity means, so let's say that uh, at infinity, so when n is going to infinity, no, let's not know it. So let's first of all figure out how we can get these three values. So we can get infinity if we, so let's say that we divide c by x. C by x will be infinity if c is a very large value. Compared to x, c is a very large value. If so, the final expression will simplify into infinity. This one I mentioned before, this one will be 0 if x is a very large value. Alright? So you can get a countable value if c and x are roughly equal. Not rough, it doesn't have to be equal, like, it's the difference isn't huge. Like in these both situations, c is very large compared to x. Over here, this is x actually, not. It's just like n. So this is x. Oh, this is x. My goodness. Yeah, there. So this is x. So in this situation, x is very large compared to. See over here, neither of them are like relatively huge. There's a difference. That's why we're getting these values instead of 1. Okay, but they are significantly different compared to the other value. All right. So what that means, okay, so if limit n goes to infinity, fn divided by gn. So I mentioned it. This can be written like this as well. So if this value is infinity, that means value of fn at infinity is a lot bigger than gn. So if I draw a graph, all right, so it could go like this. This is fn, this is gn. So that's what this means. At infinity, okay, it's like this. At infinity, value of fn is significantly larger than gn. So as you can see, gn acts as a lower bound to fn. Therefore, I can say if this expression simplifies into infinity, I can say fn is big omega of gn. Why? If you take a look at this, gn is a lot smaller than fn, which means that fn will always be below fn. Gn will always be below fn. That means gn acts as a lower boundary. Because of that, I can say gn is lower boundary using this notation. In the previous group, I mentioned big omega gives the lower boundary. So it's actually any function that is lower than, so grows slower than fn. So if this expression simplifies into infinity, which means gn can be used as a lower boundary. So big omega of gn. So the same way, if limit, so this expression, okay, and goes to infinity, fn divided by gn. If this goes to 0, that means gn is significantly larger than fn. So if we draw the graph, so it's gonna be like something like this. You can draw whatever you want actually. This will be Gn, and this will be what? Yeah, Fn. As you can see, Gn acts as upper boundary, so we can say Fn is big O of Gn. All right. So just imagine that this is a huge difference, all right? So this is like a big value over here. So we are around infinity. So the other thing is, so if this expression, yes, if this expression limit and goes to infinity, I can't write this one. Fn divided by Gn. If this goes to a value like 3 or could be 5, whatever, okay, let's write 55. So if I it simplifies into a value like this, that means there isn't a huge difference. Somehow Fn is bigger than Gn, that's why we get uh, 55, because Fn is bigger. But if we draw the graph, uh, the growth rate, there won't be much difference. They will be like growing at the same rate. So if we get a countable value like this, we can say Fn is, oh my goodness, Fn is theta of Gn. And as I mentioned in the previous group, if theta of Gn exists, we can use Gn for other two notations as well. Like this. So if it's a countable value, that means all three notations exist. If it's 0, that means only big O exists, and if it's infinity, that means big omega exists. So if I like summarize this, so let's say, oh my goodness, okay, there we go. So we have limit, and it goes to infinity. Hopefully this is the last time I will write this. Yeah, there are three possible values as I mentioned. There's infinity, there's 0, and there's a countable value which is countable. Okay, so if it's infinity, that means Fn is way bigger than Gn. That means Gn stays below Fn. Therefore, we can say Fn is big omega of Gn. Okay, what happened over here? Okay, so it's 0. If it's 0, that means Gn is significantly larger than Fn, which means Gn acts as an upper boundary. I can write Gn like this. And if it's a countable value, that means Fn is theta of like this. Okay, so if theta notation exists, that means omega and big O exist as well. All right, so if you want to try out some examples, so let's say Fn is equal to 3n cube plus uh, 5n 5n plus 7. All right, so and let's have three functions. Okay, let's say for case 1, g n is equal to n. Okay, and then for case 2, let's say n is equal to n to the power of 4, and then for case 3, I'm just gonna write 3. Okay, so 3, they're gonna say n is gn is equal to n cube. Okay, so these are like three possible candidates. So if I calculate the value, limit over here n goes to infinity, that thing. Okay, I won't be writing this over and over. Okay, it's gonna be fn divided by gn. So we can write it like you should write that n goes to infinity, but I'm going to write it over here right now. 3n cube plus 5n plus 7 divided by n, because the n is n. Alright, so this will be limit. So I get n cube as the common factor from the expression above. So I get n cube as the common factor. Okay, that's wrong. So over here, so it will be 3 plus 5n divided by n cube plus 7 divided by n cube. And over here it should be divided by n. So if you simplify this, you get these two get simplified, and you get n squared, and then inside you get 3 plus 5 divided by n plus 7 divided by n cube. Okay, so you can simplify this expression. All right, so what happens is that as n goes to infinity, so I have written it over here, but it should be n goes to infinity, as I mentioned before, 5 divided by n it goes to 0, because constant value is being divided by a very large value. Same thing with this will also go to 0. So in the end, this expression will simplify into limit n goes to infinity over here, 3n squared. All right, so 3n squared, okay, you don't have to draw the graph all the time, but 3n squared should be something like this. So as it goes to infinity, this value, this expression goes to infinity. which means, so as I mentioned over here, all right, over here, if it's going to infinity, that means the candidate gn function acts as big omega. So we can say fn big of what did we take as n? I think it's n, right? Yeah, it's n. We can do it like this. I hope it's clear for you guys right now. So let's try another one. So here we have n4. So I won't take this many steps to simplify. All right. So again, the function is 3n cubed plus 5n plus 7, which is divided by n4. Over here we have limit. So what we have is n cubed 3 plus 5 divided by n. Oh, this should be n squared, isn't it? N squared. N squared plus 7 divided by n cubed divided by n4. So this gets simplified. Over here we have n. So it will be limit 3 goes to 3 divided by n as n goes to infinity. So as n goes to infinity, 3 gets divided by a very large value. So this means this goes to 0. It goes to 0. So if it goes to 0, that means the candidate gn, which is this, acts as an upper boundary. So we can say fn is big of n4. So here again, okay, hope these two are clear. Okay, so you can use any function. You might ask, you can use any function for you that's greater than n cubed, right? You can use n5, n6, n100. Yes, that's correct actually. So any function that stays about fn acts as the upper boundary. Therefore, you can say it's big O of. You can use that function and say it's big O of whatever that function is. The thing is, we use the closest one. Okay, so let's say we have function that goes like this. Okay, so this is fn. Okay, so for this has bunch of upper boundaries like this. Okay, so this one might be n squared. This one will be what, n 15 something. This one will be n factorial. Okay, so these are bunch of upper boundaries, and it's correct if I say what fn is big O of what, n squared, and then I can say it's big O of n 15, and I can say big O of n factorial. All these three are correct. Any function that stays about fn can be used as upper boundary. Therefore, you can use big O notation with it. But we use the tightest one, which means the closest upper boundary, because that gives us a better analysis of the function. These are correct as well. They act as upper boundaries, but we use the closest one for our analysis. Okay, so you can use, instead of n to the power 4, I can use n to the power of 20 if I like, and it will also be an upper boundary. But I use the closest one. All right. So in this case 3, we have gn as n cubed. So it should be limit 3 to the power of n cube divided by 5 and divided by 7. That's 7 divided by n cube. If you simplify this, what you get is you get another n cube out 3 plus 5 divided by n squared plus 7 divided by n cube divided by n cube. So these two cancels out and these two goes to 0, so therefore you get limit n goes to infinity 3. So think of a function, okay, that will always be 3. So as it reaches infinity, this will goes to 3. So over here we get a countable value. That means that the difference between, let me actually erase this now, let's go over here. Get a countable value. That means the difference between Fn and Gn isn't significant. Therefore, we can say Fn is theta of n cube. Because theta notation exists, we can say O of n cube and big omega of n cube as well. Alright, so that's how you can use limits to find out big O and other notations. Alright, so yes, I forward a lot of stuff here in case these simplification techniques and then the concept of limits and everything. So hopefully everything is clear. If not, drop me a message and I will see what I can do. All right. So this isn't something that's complex actually. So yeah, hopefully you guys can understand what's going on. So now we know how to analyze functions using these three notations. Right. So now we need to find a way to apply these notations to analyze algorithms. So the way we can use is that we can convert algorithms into functions, and we use those functions to convert them into algorithms. Sorry, we use those functions to analyze the algorithm. So what do? We have an algorithm, we convert it into a function, and then we analyze the function, and by analyzing that function using those three notations, we analyze the algorithm. All right. So the technique we use to convert algorithms into functions is known as the frequency counting method. Okay, so if you're not familiar, it's frequency counting method. All right. So you can Google it up if you want to. So this is the method we will be using. So let's put it up there. All right. We will be using frequency counting method. So yeah, let's get started. So over here I have a very small code. Okay, so what this does is that it initializes a variable x. All right, and then it assigns the value 8 to it. Then it initializes and it assigns the value 78 to another variable y. Then this one adds the value, then prints the value to 10. So how do we do is that we count the number of operations each command takes. Okay, so here I have a command that tells the computer to initialize a variable called x. So this is this is one command. This one is one command. This one is two commands. Why? I'm telling the computer to initialize y, to declare variable y, and assign the value 78 to it. So this one is 2. How? I tell the computer add the value, then print it. Therefore, it's 2. So if I get fn of this, it's the sum of steps, which is 6. So that's frequency counting method. What you do is that you count the number of operations. All right. So this is a very simple program. Let's go to this one. So this is a for loop. Okay. So over here, I explained how a for loop works in my for loop copy. If you didn't check it out, let's go through it quickly. So how a for loop works is that, as you can see, there are 3 sections. Wait. So there are 3 sections over here, separated by this colon. All right. So what happens when the for loop executes is that, first of all, this first part gets executed. You can leave it empty. If you are not familiar with for loops, there I have uploaded a for loop video. You can watch it. It's not that long. It was like 20 minutes or something. You guys can check it out if you want to. So over here, this first part gets executed. It gets executed once. Okay. Then the for loop checks for the condition. So over here, I is 0, and it checks for the condition 0 is less than 5, which evaluates to true. So the body gets executed. So this should be 1. This is the body. All right. Okay, so the body is this. Okay. Body get executed once. So what happened? Check for the condition. The condition was true. Body got executed once. After the body got executed, increment got executed. That means i's value was incremented by 1. Now i's value is 2. Still it's true. So body gets executed, gets incremented. Then again it checks. Now i's value is 3, still less than 5. Body gets executed, get incremented. Then again checks. Now its value is 4. All right. So I get it right. 1, 2. Sorry. Oh, so now after three increments, it should be 3. Okay, now its value is 3. So at the first condition, let's go from the beginning. I messed it up. Okay. So this one gets incremented 1. Now I is 0, and the condition gets checked. So the condition is true. 0 is less than 5. So body gets executed, and then it gets incremented. Now I is 1. Then condition evaluates. It's true. Body gets executed, gets incremented. Now I is 2. Again it checks for the condition. It's true. Body gets executed, get incremented. Now I is 3. Again check for the condition. All right. It's true. Body gets executed, get incremented. Now I is 4. Then this one condition evaluates. All right. So what happens? It condition evaluates. Another one like this. Come on. Yeah. So this is 5. Okay. So because it's true, body gets incremented, body gets executed. So it should be 5. Body gets executed. body gets executed, then it gets incremented. Now I is 5. So it checks for the condition again, but this time it's false, so the for loop terminates. So if we count the number of times each one got executed, this one got executed once, this part got executed 6 times, this part got executed 5 times, this part got executed 5 times. So for this particular for loop, we can say it's the summation of all the steps that got executed. So it should be 6 plus 5 plus 5, which should be 17. All right. So over here, well, this doesn't depend on n actually. So we have the same for loop. So here we have the same for loop, but instead of hard coding the value 5, I have it inside a variable. So again, what's going to happen is that this one is literally this code I have written over here, so I'm not going to count again. Okay. So what happens over here is that this part gonna get executed 1. This part gonna get executed 6 times, which we can write as n plus 1. Oh wait, I forgot to mention something. So over here, this part got executed 5 times. This is wrong actually. Sorry, forgot to mention something. So this body got executed 5 times. Within body, this one takes 2 steps. This one takes 2 steps. Oh, sorry, this one takes 1 step. Just printing the value. So this one got executed 10 times because body got executed 5 times. Within body, there are 3. This one got executed 5 times. So the number of steps that was within the body was 10 plus 5. So the overall value should be Fn is 1 plus 6 plus 5 plus body, which is 10 plus 15. You guys can sum it up. I'm not going to do it. All right. So here, let's go from the beginning. So this part gets executed once. This part gets executed 6 times, which we can write as n plus 1 because n is 5. This one got executed 5 times, which is basically n. The body got executed n times, which means this one got executed 2 times n, and this one got executed n times. All right. So I can write it like this. Fn is equal to 1 plus this one. 1 plus over here I have what? N plus 1. Then this n. Then within body I have 2n plus n. So if I sum it up, this was going to be what? 3, then 5n plus 2. Right, so let's get right. Yeah, 5n plus 2. So this is Fn. By looking at the most dominant term, as I mentioned before, I can say Fn is O of n. It's also omega of n because On and omega n has the same Gn. I can say this one is as theta of n as well. I hope it's clear for you guys now how you can convert an algorithm into a function and use these 3 notations to analyze this function. Okay, so at the moment we are not analyzing the algorithms. This isn't an algorithm, actually. This is just a piece of code. So at the moment, when I'm trying to teach you guys is how to convert code or pseudocode into a function. All right. So over here we have two for loops. Okay. So the body. So this time is j. Body is going to get executed j times. Within j, there is another body that's going to get executed j times, which means this part will get executed j times j times. Okay, hope it's clear. So if it's not clear, I will probably conduct a copy on Sunday. Okay, so let me know and I will go through step by step. So you guys should try to do this on your own. Otherwise, like listening to what I'm saying won't help actually. Okay, so what happens is, so this is pseudocode, by the way. This isn't C, this isn't Python, this isn't anything. So if you are familiar with Python, you probably know that you don't use colon. Okay, and then again, this isn't C either. This is pseudocode. Pseudocode is there isn't a proper structure to write pseudocode. You can use it whatever the way you like. It just has to resemble a programming language. All right. So this is pseudocode. So the body of this for loop is gonna get executed j times. Within this for loop, the initialized part gonna get executed once. Condition can get executed j plus 1 times. Increment gonna get executed j times. Body get gonna executed j times, and each of those gonna get executed j times. Therefore, what we are gonna get? So this one gonna get once. Then the condition gonna get j plus 1. Increment gonna get j. So if we can say fj equal to 1 plus j plus 1 plus j plus the body. Okay, so the body gonna get executed j times 1 plus. For the initialize of this inner loop, it takes one step, and then the condition takes j plus 1 times, and the increment takes j times. Within that, it's gonna execute. So there are like 3 steps over here. So this one would be 2. So there are 4 steps. J times 4 within the loop. So this is initialize init. This part is for the condition. This j is for the increment of the inner loop, and this one is for the body. By simplifying this, you're gonna get what? Let's simplify this over here first. So what we're gonna get 1 plus 2j plus 2j plus 2 plus j. Let's simplify it first step. So this one's going to be 3j squared plus, what is this, 6j. 3j squared plus 6j, and if you simplify this, you get 3j squared plus 8j plus 2. Alright, and in order to find bigger, this should be 3j squared. So you can say fj is equal to big of j squared, big omega of j squared. j squared, and then theta of j squared. All right. As you can see, for most of these functions, big theta notation exists, which means that big O and big omega both share the same g. There are certain situations where that's not true, but for these examples, it is. All right. So I'm not gonna do the counting one by one like I did in the previous example, but this is you should get an answer similar to this. So one misconception when it comes to inner for loops is that if a lot of people say if there's a nested loop within a loop like this, all right, uh, people say, oh, I have got this wrong. So here it should be 0 j squared. Should be j squared like this. So if there's like two for loops, if there's an inner loop, people say it's big of j squared, which isn't actually true, because as you can see over here, the for loop, so over here you can see there are two for loops, but if you take a look at this, you will notice that the inner loop only execute once. This one doesn't get execute n times. Why? After executing once, we have this break command which stops the execution of for loop. So let's do the counting again. So the initialized part executed once, this one n plus 1, this one n. This one gets executed n. And here we have the body get executed n times. All right. Within here, this one gets executed once. So what happens? It checks for the condition, and then body gets executed once. After executing once, for loop breaks, increment doesn't happen. Then it goes for the outer loop again. So technically, there are only three steps within the inner loop. So it's so if I write fn, increment will be 1 for the outer loop, and then the condition will happen n plus 1 times. Then the increment will happen n times. Body will happen n times. Within body, there are only 3 steps for the increment, condition, and body gets executed once. And body gets executed once. And over here, I forgot to mention, there are 1, 2, 3, 4, 5. There are 5 steps within the body. All right. So this one gets executed 1 time. So it should be 1, 1, and 5. So 1 plus 1 plus 5. So this simplifies into what 7, 9, 9 plus 2. So as you can see, and over here this one's big O. So this one is big O of n actually, because this is the most dominant term. And same with omega and theta. So even though there are 2 for loops, this one is not big O of n squared. This is wrong. We can't say it like that. Okay, so this is wrong. So yeah, just keep that in mind, because that Manjusa might test that in the exams. Okay, so here we get into some tricky ones. All right. Before that, give me a moment, quick moment. Okay, so yeah, let's get this going again. So let's set up. Okay, so yeah, as you can see, so over here it's kind of similar to the previous one. The only difference is the increment is be multiplied by 2. So the values will be starts at 1. So after each iteration it will be 1, then 2, then it will be 4, then 8. Oh shit, should be 8. So it can be 8 and then so on. So the thing is, we can guarantee that this body is going to execute n times. So if we try out an example, let's say that n equals 5. So after 3 iterations, I is going to be greater than 5, because after after 3 iterations, after the 4th iteration, I is going to be greater than 5. Therefore, this one's going to exit. So we can't guarantee that this part, each part will execute n times. This part will execute 1 time. Okay, that's we're always aware of that. So what we can do is that we can say this one's going to execute k times. This one will execute k times. Okay, for now let's use a variable called k, and this part will execute k plus 1 times. All right. After k iterations, I has to be greater than or equal to n. So that's the exit condition. Okay. So after the kth iteration, I becomes greater than n, and that gets validated at the k plus 1's 1th condition check. All right. So this runs once, then again this runs once, then all of them run 4 times. After running 4 times, it will be 8, and after running the condition check for 5th time, only the loop will exit. Therefore, after k iterations, I will be greater than n. All right. So I can after k iterations, I can say I is equal to 2 to the power k. That's k. Okay. I can say it's 2 to the power k. So by substituting this, so like over here 2 to the power 4. If you don't understand, just substitute a value instead of using a variable. So by substituting this, you can say 2 to the power of k, it has to be greater than or equal to n when the for loop exits. So I can use logarithms here. I can say log 2 to the base 2 to the 2k greater than or equal to log 2 to the power n. By simplifying this, I get k. K has to be greater than or equal to log 2 to the power n. All right. So if you write fn, no, let's simplify this first. So this says k has to be greater than log 2 to the power n, but at the same time k has to be an integer. Right? K is the number of iterations. Therefore, k can't be a float, but it has to be an integer. That means we have to either get the ceiling value or the floor value of this expression over here. Either we have to get the ceiling value or the floor value in order to make it an integer. Because as you might know, look, base 2 doesn't always give integer values. Sometimes it gives decimal values as well. So in order to make it an integer, what we have to do is that we have to find k value that is an integer, and the lowest value that will greater than or equal to log n will be log 2 to the power n, and get the ceiling value. So this notation means ceiling value. So like if I have like 5.2, ceiling, this will be 6. Same way that there's floor as well. So let's say that's 4.8. This gives the floor value. This will be floor. So this takes the closest integer. So ceiling will always go to the upper bound and floor will go to the lower bound. So if you take a look at this, ceiling value of log 2 to the power n will always be greater or equal to log 2 log 2 to the power log base 2 8. Okay, so if we like substitute values, so if for some reasons undo isn't working, I don't know. So if we take log 2 to the power n equals something like 0.35, in that case, the upper boundary will be greater than this value, but if it's an integer, this will be equal. So therefore this value satisfies this inequality. Therefore we can say k equals this value. And if we try to write fn, okay, I will write it down here so it's easier. Fn using k, so it will be 3k plus 2. Over here I have the value of k, so I can write fn equals 3k plus 2. By substituting this, I can say 3 log 2 to the power n ceiling value plus 2. So that's fn for this. Alright, hope it's clear. So yeah, let's move on to the next one. So here we have I as the iterator, but we check the condition for j. This is an I. Alright, again we assume this body executes for k iterations and increment happens for k iterations. Which one? Over here. The condition check will happen for k plus 1, and over here this one will always execute once. So we can write fn using k 3k plus 2, yeah, just like previous value. And after k iterations, I can say j equals 0 plus 1 plus 2, and it goes up until k. Alright, so there are k number of values here. So I can say j is equal to k divided by 2 k plus 1. So the summation can be simplified into this expression. Okay, so if there are like n number of elements, I can write it like this. So if there's like 1 plus 2 plus 3 and it goes up until n, I can say this is equal to n divided by 2 n plus 1. That's literally what I'm doing over here. So instead of n, I use k over here. Okay, so I'm going to use this. Okay, so k over here, and I can say j is equal to this. So after k iterations, if you take a look at the condition, j has to be greater than n after k iterations, and I can say j is equal to this value. Therefore I can say, let's write it over here, k divided by 2 times k plus 1 is greater than n. So if I simplify this, I get k square plus k minus 2n greater than 0. So now I need to find the values of k. Alright, so in order to find the values of k, there's what I don't remember the name of the that term. So you might have done this in Oliver class. So b square minus 4ac divided by 2a. So some of you might remember this. Okay. So we use this equation to find the values, possible values of k. So k will be so it's minus 1, so minus 1 squared minus what is it, minus 4 is 1 and c is minus 2. Let me just rewrite this. So you can write it as minus 4, 1. It's actually minus 2n. It's divided by, this is minus 1. It's not clear. It's divided by 2. So by simplifying this, we get the values k equals minus 1 plus o equal what is it, 1 plus 8n divided by 2. Okay, so I can say case k is either equal to minus 1 minus 1 plus 810 divided by 2, or I can say k is equal to minus 1 plus 1 plus 8n divided by 2. So k has to be a positive value. Okay, k is the number of iterations, therefore k has to be a positive value, and as you can see, this one will never be a positive value. Therefore I say k is equal to 1 plus 8n minus 1 divided by 2. Alright, so that's the value of k. Okay, so to satisfy this equation, so the inequality was this. Okay, so if we write that down over here, k divided by 2 k plus 1 has to be greater than n. So because of that, what we do is that again, this one can give non-integer values. In order to find the integer value, what we do is that we find either floor or the ceiling value, but because this one is always greater than n, what we do is we get the ceiling value and then we add 1 to it, because this will always be greater than n. Okay, this is k. Or you can use this as this. You can't use this one as k because k has to be an integer. So you have to use this as k. This will guarantee to be bigger than n all the times, because this has to be n. You can't use the ceiling value because if you use the ceiling value, k will be either equal or greater than. In this situation, it can't be equal. It always has to be greater than. Therefore, we use the floor value and then plus 1. And then we have to substitute this to fn. Okay, I'm not going to substitute. You can do it on your own. So fn is equal 3k plus 1. So plus 2 it was. and you can substitute this and get the effect. Okay, and then we have this. It's the last one. No, that's not. Okay. So in this one is very simple actually. So this one is what we have. We have this. I'm not going to do this because this is very simple. We have this normal for loop out as the outer loop, and this example as the inner loop. Okay, you over here you see we can I is multiplied by 2 after iteration. That's happening over here as well. So all you have to do is you have to get the value of this and multiply it by n. Okay, that's all. Do it on your own, and if you have any problems, just drop me a message. Okay, I'm not going to do it because it's very simple. All you have to do is just multiply and add those values. Then we have this one. So instead of multiplying by 2 over here, it's been divided by 2 after each iteration. All right. So again, I'm going to say the body is going to get executed for k times. This one will execute k times. The condition will execute k plus 1, and this one will execute once. Therefore, we can say fn is equal to 3k plus 2, just like before. All right. So after k iterations, what is it? I has to be greater than what? I has to be greater than 1 after k iterations. Sorry, I has to be less than 1, less than or equal to 1. Sorry, got it wrong. So as long as I is greater than 1, this gets executed. But the moment I gets less than or equal to 1, it gets terminated. So k is the number of times the body got executed. Therefore, after k iterations, I has to be less than or equal to 1. So after k iterations, I starts at n, and in each iteration it gets divided by n. So after the kth iteration, I can say I is 2 to the power k less than or equal to 1. Sorry, oh yeah, 2 to the power of k. All right. So we can say what n is less than 2 to the power of k. So I can say log 2 to the power n has to be less than or equal to k. So k has to be greater than or equal to log 2 then. So again I can say k is equal to, this time it has to be, did I get it wrong? If it's scaling value, give me a moment, I think something's wrong. Okay, so I found the mistake. Over here this should be k minus 1. So so how this goes is, in the first iteration, okay, in the first iteration, i's value is n. Okay, then it gets after body gets executed first time, it gets divided by 2. So for the second iteration, I is, so it should be n. I is equal to n, and in the second iteration it's 2. In the third iteration it should be n divided by 4. So which is equal to what, squared. In another way you can say n divided by 2 to the power 3 minus 1. So same way, this has to be k minus 1 instead of k. So now what we have is log 2 to the power n, log 2 to the power n plus 1 has to be greater than k. So k has to be greater, therefore we get the ceiling value. Log 2 to the power n plus 1. And you can then substitute this to this function and get fn. Alright, so a little bit of math is involved. Hopefully you guys are familiar with those basic math concepts. If not, then take some time to revise. Alright, so that's frequency counting method. That's how you can get an algorithm and convert it to a function and use that function. We can use that function to analyze we can use that function to analyze the algorithm. Okay, so let's see how we can use it to analyze algorithms here. Okay, so it's loading. Oh, this is 1.3. It keeps changing. Okay, so yeah. So over here we have a small algorithm. Okay, so let me slow it up. Okay, there we go. So this is known as a linear search or a brute force search. So what this does is that I have this array of these elements. So I have a target of 66. So it's gonna go through each element and see whether the element array I is equal to the target. If it is, then it prints the index. So it tells me where the target is located. So it should be 1, 2, 0, 1, 2, 3, 4, 5. It should print 5 because it's in 15th index, and then it breaks the loop. Alright, so this is a linear search algorithm. So we can we can say that the body is gonna get executed len times, and this one is gonna get len 1, and this one is gonna get executed len times. You can write that, but that's actually not correct. You can't say the body is going to get executed len times here because we have this break statement. So once this condition is satisfied, the for loop is going to break. So what we are doing in frequency counting method is we are trying to figure out how many steps this program will take. So if it's like a simple for loop where you are sure that it's going to go through each element, then you are sure that the body is going to get executed n times. But over here we have this break statement inside. Therefore, we are not sure whether it will execute. Over here it's len, not n. Okay, that many times, or is it gonna break before? So it's like, think of a scenario. So okay, so think of a scenario. Forget about this for a moment. Think of a scenario, okay, where you have a bookshelf which has 50 books, and you have to find a book, but you don't know where the book is. So what you're going to do is that you're going to start from the beginning and going to go through each book until you find the book you're looking for, and then once you found the book you're looking for, you're going to stop looking because there's no point. All right, so think of a simple scenario like that. So like when you're looking for that book, imagine yourself, what is the best possible thing that can happen? So you open the bookshelf, and then so let's say that's a closed bookshelf, so it's closed by 2 panes or something. So you're gonna start looking for the book you want. So the best thing that can happen is that the first book you take out is the book you're looking for, so that you don't have to go through all the books. Just one step, and you found the book you're looking for. That's the best thing that can happen. All right. The worst thing that can happen is that you will have to go through all the books, and the last book you take out is the book you're looking for, or either the book isn't in the bookshelf. So that you went through all the books, but you didn't find what you were looking for. But somehow you went through all the books. You went through all the 50 books. So, in a best case situation, okay, it doesn't matter how many books are in the bookshelf. So, let's say that for the previous example, you checked a bookshelf with 50 books, then you are going to check one for 100 books. Even then, you are going to take only one step to find for the best case scenario. You only it only takes one step. The best case scenario is finding the book. The first book you take out is the book you're looking for. On the other hand, worst case increments as the number of books in the bookshelf. So in the first scenario, there was a bookshelf with 50 books. In the worst case scenario, you had to go through all the books. That means you had to go through all the 50 books. In the second case, there's a bookshelf with 100 books. And in the worst case, you have to go through all the books, which means you went through 100 books. So let's say in the third scenario, you have a bookshelf with 150 books. So then in the worst case situation, you have to go through all the 150 books. But in the worst case, it was always one. So what we do is that when we are analyzing an algorithm, so that is an algorithm. So the method you decided to find the books is known as an algorithm. So you said, okay, I need to find this book. So what I'm going to do, I'm going to start from the top left corner and gonna go through each book until I find the book. That is an algorithm. Okay. So how we analyze the efficiency of this algorithm is that we draw two graphs. We don't technically draw graphs. We create functions. Okay. For the sake of understanding this, let's draw a couple of graphs here. So you draw two graphs. Okay, so this is number of steps you take, and this is the number of number of books in the bookshelf. Okay. Sorry. Okay, so let's draw another one quickly. I don't know what's wrong with this. Okay, let's draw another one. Okay, so this is again, I'm gonna call it test. That's easy. So it's S, and this is S stands for number of steps, and this is N number of books. So this is the best case scenario, and this is the worst case. For the best case scenario, no matter how many books in the bookshelf, you will always have to wait. In the best case scenario, no matter how many books in the bookshelf, you will only have to take one step, because the first book you take out, that's the best case. First book you take out is the book you are looking for. So it doesn't matter how many books in the bookshelf, you will only take one step. In the worst case scenario, you will have to go through all the books. That means it increases linearly as the number of books in the bookshelf increases. All right. So as you can see, this function is fn equal 1, which means it's constant. So this can be any constant. This can be 1, 2, 3, 4, 10, 100, anything. It has to be a constant, that's all. So this function fn is n. It can be n, 2n, whatever. Okay. So over here we have two functions. So let's use different function names. For the best case function, I'm going to use b of n, and for the worst case, I'm going to use w. Okay. So As you can see, b of n is 1. Therefore, I can say b of n is big O of 1. Why it's a constant. Also, I can say it's a big omega of 1. So over here, this one and this one means two different things. Okay, even if this was 100, so let's say hypothetically this was 100 instead of 1. Even then, this will be big O of 1. Big O of 1 means that the function uh, is a constant. So even if it goes like from here with the value of 200 or 300, even then I will use big O of 1 to say the class it belongs to is big O of 1. So the point of big O notation and other notations is to find the class a particular function belongs to. And this function and any other function that has a constant in it belongs to this constant class. All right. So over here I say big O of 1 and big omega of 1, because these two share the same gn, I can say big theta of 1 as well. And this is the worst case scenario. Worst case scenario, we had w of 1, wn. I can say it's big O of n, and you can say big omega of n, and then you can say big theta, not big theta, just theta of n as well. So as you can see, so there's another case I need to talk about, which is known as the average case. I will talk about it later. So over here, just focus on these two for a moment. As you can see, I used all three notations to describe both best case and worst case scenarios. So sometimes if you have taken an online tutorial or something, some people say that big O is what we use to analyze worst case scenario, and big omega is what we use to analyze big omega. Sorry, big omega is what we use to analyze best case scenario. That's actually not true. Okay, best case and worst case are used to analyze the algorithm. We create functions for each case, and to analyze each case we can use any of those three notations. So big O gives the upper boundary, big omega gives the lower boundary, and theta gives the growth rate. All right, so big O tells us the function fn will never grow faster than this. So it will never go above this upper boundary. Big omega tells us the function will never go below this lower boundary, and big theta tells us the function will grow as fast as the function gn. So same thing over here. Okay, so same thing applies to this as well. So this is a linear search algorithm. So the same thing we did to find the book. Okay, let's clear off this. So instead of finding the book, we look for a number. So the best case could be, instead of 66, this is 1. If this was 1 instead of 66, that's best case. That means the first value we took, the first value we take out, first value we check is the value we are looking for. The worst case is that this could be either 98 or a value that doesn't exist, like 100. So if the target is 100, we would have to go through all the elements in the array, but somehow that doesn't exist. So somehow, but either way, we went through all the elements. All right. So in the best case scenario, I can say it is 1. Therefore, I can get big of, sorry, it should be big of 1. Over here it's a big of 1, omega of 1, and then theta of 1. All right. So this is b actually. Okay, and then best case, and then the worst case, the function is n, and then therefore big of n, omega of n, and theta of n. So these are the best case and the worst case scenarios, and we know that in an average situation, finding the element would be in between somewhere here. It's not the first element or the last element. It's most probably one of these elements, like one of the ones in the middle, like this situation where 66 it's almost in the middle. So for that we used average case scenario. All right. So in an average case scenario, what we do is that we sum up the number of steps it would take to get each element, and then we divide them by the number of elements. So what I mean by that is, so to get the first element, I would take uh, only one step, only one iteration. Okay. And then to get the second element, I would have to go through one and then check for second one. So I would have to go two steps. To get the third element, I would have to go one, then second one, then I will have to go, then I will arrive at the third one. So it will take three steps. Just like this, it will take n steps to get the nth element, and then we are gonna divide them by n. So this gives us the average case function. This should be a. It looks like a cube. Okay. So the summation. So we can simplify this. Divide by n. How should we divide by n? Divide by n, and then this summation can be written like this: n plus 1, and then this can be simplified into n plus 1 divided by 2. So this is the function for the best case scenario. So I can write it like n plus 1 divided by 2. All right. So this is the function. This is a. So by looking at this, I can write it like this also. So earlier in the group, I mentioned how to find the big O notation. So big O notation, take the most dominant term, which is n divided by 2, and remove the coefficient. So we get n. And the big omega, same way, n. Because these two share the same gn, I can say big theta of n. So that's how you analyze the algorithms. So what you do, you take each case and then you create a function. Okay, this in this situation it was bn equals 1. For the worst case it was wn equals n, and for the average case it was n divided by 2 plus half, 1 divided by 2. So you create a function and then you analyze that function using those three notations. All right. So that's how you analyze the algorithm. So yeah, if someone says that big O gives us the worst case and big omega gives us the best case, theta gives us the average case or something like that, that's absolutely incorrect. Because those three just gives us boundaries for a particular function. So what we have to do is that for each, we need to know each case. Okay. So for this algorithm, so this is a search algorithm. For a search algorithm, finding the element as quickly as possible is the by using the least number of steps is the best case. So let's say there's a sorting algorithm. For sorting algorithm, the best case is that the input array is already sorted. So you have an array with a bunch of elements, and then you feed it to a sorting algorithm. The best case for the sorting algorithm is that the input is already sorted, therefore it doesn't have to do anything. So worst case is that this one is sorted in the opposite manner. So let's say that I have a sorting algorithm that sorts the input array in ascending order. So the best case is that the elements are already sorted in the ascending order. 2, 3, and 4. Worst case is that they are ordered in the descending order. So it actually depends on the algorithm. All right. Another thing, okay, so you might mix up over here. For the average case, for this situation, this is the function, but this isn't the function for
all the algorithms. Okay, so these are only examples for this simple function. So for this simple algorithm, okay, base case isn't always equal to one. There are certain situations where base case is equal to n, and the worst case is equal to n squared. All right. So for this, so these are like for this example, we have these values for bn, wn, and an. But for other algorithms, it might be different. So especially this one. Okay, so like it's only valid 1 plus 2 plus 3 plus until n is valid only for this. So what you have to remember is that you have to sum up the number of steps each element would take. So let's say there's a function which takes what square times. So let's say that average case in a certain situation is 1 squared plus 2 squared plus up until n squared. And then you divide it by n. You always divide it by the number of elements. The only thing you have to change is that you have to figure out the number of steps to get each element, and then you sum them up, and then you find the average. So this one will not simplify into this. That will not happen. Okay. So those are the areas you might mix up. So my suggestion is do some questions. And if you have problems, drop me or uh, someone who might know the answers a message. All right. So yeah, that's pretty much it for this for the algorithm analysis. It took a little longer than I expected. Actually, it's almost 2 hours. I was expecting to finish this within an hour. So after this, I will see what I can do. All right. So yeah, that's it. That's it for this video. Hope you guys have a great day.